Hey everyone, welcome to this module on computer forensics that we're going to talk about Windows forensics this time. I'm DSP. So in this module I'm going to talk about the registry, which is a database that Windows has. Then we're going to talk about recycle bin forensics. We're going to mention some properties of thumbnails on Windows. We're going to talk about browsing history, printing, printing jobs when you print a file and the traces this might leave on the system. And finally, we're going to talk a bit about the event trace subsystem for Windows. So for the case of the Windows registry, it is a hierarchical database, meaning like it is a tree-like and a rooted collection of keys and values. Um, that describe properties of the operating system, the application installed, the whatever configuration that might be persisted for the user settings, security properties, and many other things on Windows. It is really treasure trove for forensic information. And also it is a very important part of the system that malware can try to affect, so we need to know our way around it. As you see on the thumbnail that I have here, you can see that there are various, on the left side there are various keys, and they're kind of named, most of them like H key, like Hive key. H stands for Hive in this case, and then some other names. So for example, on the top we have HKey classes root, HKey current user, HKey local machine, and more keys like that. But that doesn't mean that all registry keys are named like that. So on the right side of this, you can see that we have certain names of that key value pair. We have a type, so this can be strings or words or integers, various types of values that we can persist on the registry, and then the actual data that it has. So let's see an example here. For example, the current user, it has a registry string that is of that has value username, as we say here. So the registry is persisted in files on the disk, and then whenever a part of the registry is edited, for the time that it's edited, there is another file that is created called a log file, and you can find that by .log extension, and that file keeps the temporary state of the registry before it is merged back to the rest of the registry. So you can imagine that you can treat that those files as something that you can examine with the standard file system forensics techniques that we have learned. Okay, so you can undelete them, you can extract their temporary state by the log files and other usual file system forensic stuff. Now, also as I mentioned here, all installed programs have values that are persistent in the registry. A lot of game hacks, for example, in previous times, because now games are more advanced, but a lot of game hacks of the past involved editing values in the registry so that you make the game believe that it is, it hasn't, it's still on demo period, or, if you're using a shareware program, that it's still valid, and other things of that sort. So, as I said before, the registry is a collection of hives. A hive is just a set of a group of keys on the registry, and a registry hive is persisted as one file. Okay, you can find most system-related hives under C Windows System 32 config. Okay, and some famous hives that I mentioned here is the SAM, which is a system account manager. Okay, so SAM contains all the info that you might want for your installed accounts on the system, and also the password hashes for these accounts. Okay, equivalent to /etc shadow on Linux and /pastwd. We also have the security hive, which contains various policies for the system, and also the cache credentials. That's very important. And we have software, which is, as I mentioned before, the set of installed programs, okay, and nt-user.dat, which is a user-related Hive, and that contains user-related settings. So, for example, what programs a user might want on their startup, for example, or the recent files they opened. And nt-user is a relic from the time that this was implemented on Windows NT, so that's why you see nt-user here. Now, as I said, the hives are we see them here as files, so each hive is a file that is persisted. But if you see here on the next slide, now these files turn themselves into sets of keys, as I mentioned before. So, for example, the system hive can become the key known as hkey_local_machine that we see here, okay? Or the, as I mentioned before, the things from the SAM hive might end up into hkey_user or hkey_current_user. So what is hkey_local_machine again? It is now the on memory, let's say, registry key, hive key that pertains to things that have to do with the local machine. So, for example, the installed programs. Or another interesting property here is all the history of devices that have been plugged in and plugged out of the system. So, if you want to see if a certain USB drive has been plugged in the system, you can just look into hkey_local_machine, and then you can see the history of device connections that have happened on that system. So you can prove if a user has accessed a certain thumb drive or not, for example. Now for the hkey_current_user case, we can find the URLs that they typed in their browsers and the recent files they have accessed. The hkey_user hive relates to all other users apart from the current user. Okay, so you might find info on all other installed users of the system. And then another important one is the classes root, which kind of keeps the association between file extensions and applications to be run. I mention this here because it's a frequent target of malware, because you might have malware installed that the next time you click, for example, a .eml file that would open up an email with Outlook on Windows, you would have some sort of malicious program parsing it and, for example, installing themselves on your mailer program. Here I mentioned some videos that you can go and take a look to learn more about the registry generally, but more importantly, I mentioned a tool here called Registry Explorer, which is a standard tool that you should learn to use, and you can you can see the status of your own registry on your system if you run Windows. So let's go to recycle bin forensics. Now the recycle bin it's a pretty obvious construct here. Every time you delete a file, you don't really delete the file. It just gets moved to a temporary folder, and then it expires if some time passes. So if you're wondering why you deleted some files yet you didn't free up any space on the system, it might just be because the files are moved to the recycle bin and they haven't actually been deleted. Now on the typical Windows system, if you press Shift Delete, that kinda says to the system, please delete it completely, I don't want it to go through the recycle bin. So Shift Delete should normally delete a file. Of course, we also mentioned that in the previous modules, deleting a file doesn't really mean on NTFS or FAT, it doesn't really mean wiping out the data, right? It just marks the file as deleted, frees up the space, but then probably the data blocks are still there to be inspected. So, in NTFS file systems, okay, the recycle bin is a subfolder under the user's home that is created with a security ID. Up to Windows Vista, this recycle bin folder contains certain records called Info2 records, and these Info2 records are metadata, so they will let you know of the deletion time, the original file name that the file had, the path that was in, and other things. Okay. Now, as I mentioned before, if you press Shift Delete, normally it shouldn't go through the recycle bin. So if you press Shift Delete, you should not find an Info2 record of that file. From Microsoft Windows Vista and Dawn, we have a hidden folder called $recycle.bin. Okay, we don't have any more info2 files. Okay, and then you can see here every deleted file becomes a pair of files. That is the actual deleted file that has the data. Okay, and then another file called .i blah 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 .txt. The XXX here is the name of the file. That is the metadata. Okay, which is very similar to what Info2 had. You can check out this video for more info on recycled bin forensics. Needless to say that if you are analyzing a Windows system, looking at the recycle bin should be one of your top priorities. Now, talking a bit about thumbnails. Thumbnails are files that are created that contain a shorter, a smaller version of an image that is present on the system. So, if you have an image on your system and you go through, for example, the grid view of your File Explorer on Windows, you see smaller versions of your image in a grid layout, so you can choose the image that you want. This is thumbnail. Okay, so it means the system, when it finds out about an image, it creates the thumbnail and it stores that somewhere. Okay, why do we mention this? Because these thumbnails, when you delete the original image, they are not typically deleted. So if a user has, let's say, nefarious images on their computer, the thumbnails that have been created for those images are probably still persisting on the system. You can find the thumbnails under this path. Okay, and there are, let's say, database files that have cached thumbnails images. Okay, actually there is a pretty interesting case involving a Norwegian man who was downloading child pornography, that he was and he was actually convicted because thumbnails of the images were found on his computer. Also, link files are equivalent to our Unix symbolic links in this case, and whenever Windows, whenever a user on Windows opens a file, this link file points them back to the original file that is linked. Now, the important thing for these link files are sometimes they are again used by malware, and I'll explain how. Now, link files are usually contained in these paths that I mentioned here. So, for example, for Windows 7 to 10, they are in C users, your username, update are on Microsoft Windows Recent, okay, and for Windows XP under here. Now, link files, as I said, might be used for by malware to point to content that they want to be executed when at some point, and then these link files find themselves into startup scripts. So you might have your startup script that is running various commands on your system, and then you might see there, instead of a command, a link file, and that link file will point to the malware. But the link file might look pretty not suspicious, because it might be in a path that you would expect it to be, but that might point back to the actual malware that is, something bigger installed in some weird place in your system that you would kind of flag it if you saw it execute like that. That's why I mentioned before that link files can be kind of abused by malware in this case. So these link files can be either created automatically by Windows by program installers when you install a program, or a user can actually create a link file for their convenience. Okay. tools like FTK Imager and read these link files, and then they can also follow the link and tell you if that link still is valid or not. Okay, check out this link for more info on analysis of link files. About browsing history, this is a bit of a giant topic and that deserves its own module, but I'll just mention briefly here that both Firefox and Chrome maintain their browsing history in the SQLite databases. SQLite is a tool that it's a library that creates databases that are completely persisted on a file. So you can go and download a tool called SQLite Browser, and that is available for most operating systems, and that tool will allow you to visualize contents of an SQLite database. Then you can find online or ask me in Discord, and I can point you to the standard locations that, depending on your browser, this SQLite database have been persisted. And from there you will be able to see mostly everything that has that is on your web browser. So for example, you will be able to find your of course bookmarks, for example, your latest visited sites. You will find things like the links that you followed from which site to which site. You will find things like, of course, your downloads. You will find things like your saved passwords, like if you save your passwords on the browser. And just to mention here, if you choose to save your passwords on the browser, you should absolutely encrypt this password with master key. Okay, I'm not sure if Chrome does that automatically, but I think Firefox did not do that automatically. So if you don't do that, then whoever uses just, you can honestly just use strings, and then you would see your plain text passwords on the SQLite file. So you need to make sure that you use some sort of encryption addressed key there, so that your passwords are at least encrypted addressed in that SQLite database. So for Internet Explorer, as I mentioned here, there is another tool called Pasco, and you can use that to examine all the things I just mentioned here. Now we also need to talk a bit about private browsing and what is private browsing in that sense. Private browsing normally should just not persist files on these databases here, so it shouldn't persist the state of your browsing once you turn on private browsing in these databases. So it shouldn't log in the sites that you visit in the visited sites, or the downloads that you made while you were in private mode into these files. However, that doesn't mean that your activity is private in any more sense when seen from the server. The server that you connect to still knows that you're connecting there, and the server that you connect to has no concept of you wanting to browse in a private mode. So all your activity is still logged in and persisted server side, technically, though it is not persisted on a file on your disk while you browse. Check out this video again with some obvious info on private browsing. So printing now. When you send a print job, like you see, you have an email here that you read it, and then you click, right-click, print as, and you send it to the local printer. You should know that this leaves too much information laying around for an investigator. First of all, on that file, on that system, there is another file created called a shadow file. Okay, and that shadow file kinda is there until that print job is completed. Okay, so it's great there in case something happens to the original file, but you still want to print it and the printing hasn't happened yet. That shadow file is going to make sure that the contents that you're printing are still there. Also, there is the spool file, which has info on your current printing job. So, for example, you want to print this data and you want to send it to that printer, and you started this action back then, and it still has not completed. All that is persisted in the spool file. Okay, and we also have some link here for a video that is using this whole spooling system on Windows to showcase vulnerability in that spooling system on Windows. So there, for example, was an vulnerability in the printing subsystem that allowed anyone to submit a job, and through that job to actually hack the computer that was accepting the job and gain administrator access on that computer. You can see that video here. And of course, print jobs, evidently, as I mentioned from here, are persistent in many places. So if you actually printed something, chances are that this file will be way more recoverable because it has found, the contents of the file have found themselves into many more locations around here, around the disk of the system and the network. And another place they're going to really find themselves also in the memory of the actual printer. You know, these printers are normal computers that have memory and they run operating systems. So whenever you send something for printing, that content is also persisted on the printer, of course. Here, I just point a link for you that is from SANS that has some very good info on general Windows forensics, and you can use this as a reference whenever you are working with a Windows system, but it requires for you to create a SANS account. Now finally, I want to talk a bit about the event tracing subsystem, event tracing for Windows, ETW. Okay, and the event tracing subsystem is a very high performance persistent logging system that Windows has. It allows a group of producers and consumers to communicate through that system and persist information, trace information about processes. And this can be used both for debugging purposes, but also for just day-to-day work. And so through that subsystem, you can, as a developer, send tracing notifications to the system and then consume these tracing logs and see if your application is going correctly. That is that was a main drive behind it. Okay, and you can imagine that because it is it encompasses the whole Windows operating system here. You can get tracing logs from many different subsystems of Windows, and you can reason about what's happening. Again, check out these links for more tools to work with it, but generally the structure is a controller. Okay, the controller is someone who instruments that subsystem. Okay, and you can start a tracing session. Okay, or stop the tracing session, or enable a data provider. Okay, and what is a provider here? A provider is what we really care about. Is a system that produces events to be logged. Okay, these events go on a queue that has buffers. Okay, to be able to buffer many events together and not get stuck, so that more providers can keep logging, right? And then also it has consumers, which normally is a program that reads these logs for you. Okay, and it gets back data from these buffers and empties them. Okay, these events can also go into log files, of course. So again, the controllers, remember the controllers, you start and stop sessions, and they can define things like the location of the log files that they want all these events to be logged. Okay, important here as again enable the providers, okay, manage things like the size of the buffers that are in this pool, or get statistics for the sessions. The statistics, as mentioned here, would involve how many buffers are used and events that might have been lost in the system. The providers, which is what we care, are the applications, okay? And to be a provider for the ETW, you need to adhere to these APIs of ETW and give back data from your own instrumentation through these APIs. Okay, you need to be able to register yourself as a provider, so the controllers can turn you on and off. Okay, and also another important thing here is that applications can include controllers and providers themselves. Okay, so applications can include can turn on other application can turn on other applications, right? Because an application can include a controller. So you can imagine this can be pretty recursive here for big applications, right? The consumers, which are the parts of the system that are actually getting out data from there, and they can subscribe to certain flows of events. Okay, they can get events stored in either from live sessions or from log files, or they can observe many sessions concurrently, right? And if you do that, then you should get the systems back in chronological order as they happen. Okay, but you can also look back historically, then you would still get back the data in chronological order, although you might be observing multiple sessions, right? And you can see how this has now forensic value, because you can be observing a system that has to do with the disk, and another system that has to do with the memory, and another system that has to do with the network. And then by observing these three subsystems and getting the events in a chronological timeline, you actually have a timeline of the events made for you via the ETL. Okay. Now I mentioned here some ETL files that have forensic value. Okay, so boot events, for example, or loading of drivers, you can find them over here. Okay, Wi-Fi connection history. This is super useful here on a laptop, right? Because by looking at these ETL logs of Wi-Fi connection history, you can, for example, infer where physically the laptop has been moving around, right? Because you saw these Wi-Fi networks now, and then these Wi-Fi networks later, and these Wi-Fi networks after that. And you can infer the path of a user having that laptop, physical path, right? And then of course these kernel power events that can tell you when the system was put to sleep, when they connected it to an outlet, when it was running on battery, and all that stuff. Okay. Finally, some ETL providers that we care about is, for example, the Windows kernel process. Okay, this tells us all the processes that were created and when they were created and when they were also terminated. Okay, along with their command line. So you can imagine it's like if we were forking, processes and had options when we were executing them. All that would be persisted here in this ETW log. Okay, and then of course if that process fired up another process, that would also be persisted. And Windows kernel file would tell us everything about what we want for files, when they were created, deleted, or modified. Okay, and Windows kernel network, again, all the network connections that we want, and DNS queries. So whenever we queried something from the browser, or we pinged something, or we a program that we executed looked up a host name, all these DNS queries would be persisted in this ATW logs. Okay, and finally, Microsoft Windows PowerShell is important because a lot of malware packs the shellcode that they want to execute as PowerShell commands. So when we suspect that the system might have had shellcode running on it, by inspecting this ETL logs that have to do with PowerShell execution, we can see what scripts were executed. And most of the time for Windows malware, you will find something interesting in this part of the logs here. Finally, guys, this is a fantastic video. I think it's from Sans that you can watch about ETL generally. So I'm not going to spoil for you, but I highly advise everyone to go and watch this video. It's a fantastic presentation on the fantastic wealth of information that we have using ETL. This was a very, very short module on Windows forensics. I hope you see that Windows has a way more complex structure than Linux, but also offers a way more structured way to approach forensic on the system. For example, the ETL subsystem that we have here is a way more structured system than just a syslog on Linux that some programs might want to follow and others might not. However, that being said, that doesn't mean that the programs on Windows all follow these nice APIs and actually log stuff through ETL, which kind of turns that argument back and says, okay, the same thing happens on Linux, right? Not everyone logs properly through syslog. Again, there. So it really depends on the application developer to do that. Now, both Windows and Linux offer tools that can trace processes even when these processes don't adhere to the API, but to a certain API. But that would incur way more overhead on the system, and usually this type of tracing is turned off. It's only turned on for debugging, right? You wouldn't run a normal program on Linux, for example, using systrace on it, because strace, because you would have just too much logging happening, and your program would run really slowly because every time you would need to log a system call when you execute it. For the same reason, although also Windows offers a very similar function, tracing subsystem here, it usually is not turned on because it really slows down programs. Thanks for watching this little module, guys, and we'll see you next week.